Among all the wireless power transfer technology, the most widely used and mature one is inductive coupling. Key standard which defines wireless power transfer using inductive charging was released in 2008. When the first class of mobile device wireless chargers emerged in 2012, the response was huge. Now wireless charging is so widespread that we can find this technology around us easily. For example, if you're an iPad user, every time you put your Apple Pencil back, you're actually wireless charging it. When we dismantle the Apple Pencil, a coil is shown. So, what is a coil used for? To explain this, we need to trace back to 191 years ago, when Faraday firstly discovered the law of electromagnetic induction. He discovered that when there's a change in magnetic field, an electromotive force will be induced in the electrical conductor to oppose this change. Transformer, which is used to switch an alternating input voltage into lower or higher output, worked based on this law. The alternating current in the primary coil produces magnetic field continually alternating its direction, and magnetic field is passed to the secondary coil through an iron core to concentrate the field. Hence, there's a constant change in magnetic field and output voltage is induced in the secondary coil. Electrical energy is transferred without the two coils directly connected together. Inductive coupling works on the principle of the transformer. The only difference is that there's no iron core in the middle of the transmitter and receiver, which means the magnetic field produced by the primary coil cannot be concentrated. It means distance between the two coils need to be very short, or the efficiency will be very low as a result. Inductive coupling has been successfully applied in all kinds of areas, one of which is wireless charging of vehicles. A few days ago, I got a chance to visit a vehicle wireless power transfer project of US students. They designed a system to charge vehicles by inductive coupling. According to the developers, the efficiency can reach as high as 90%. However, it's under the premise that the two coils are accurately matched together, which is very hard to achieve for some other applications. One of these applications is electronic medical implant. It is definitely hard to match the two end coils with each other precisely. However, wireless charging for medical implants like pacemaker has significant meaning as it can avoid the suffer to run the wires through the skin and also reduce the risk of electrical shock due to exposure of wires. So, what are the other methods we can use to address this issue? One of the feasible improvements is resonant inductive coupling. The main difference between it and normal inductive coupling is that the two end coils are changed to the LC circuits, which consists of an inductor and a capacitor. When an inductor is connected across a charged capacitor, the voltage across the capacitor will drive a current through the inductor, building up a magnetic field around it. The voltage across the capacitor falls to zero as the charge is used up by the current flow. At this point, the energy stored in the coil's magnetic field induces a voltage across the coil. This induced voltage causes the current to begin to recharge the capacitor with a voltage of opposite polarity to its original charge, and complete the other half of the cycle. The energy is stored as magnetic energy in the inductor and electrical energy in the capacitor. The forth and back of the energy and current is like a pendulum doing simple harmonic motion. The system has natural frequency, which is a frequency at which it will oscillate when isolated from any other system. If the external applied current has a circuit's natural frequency, resonance will occur, and a small driving current can excite large amplitude oscillating voltages and currents. Now let's come back to the resonant inductive coupling and look at it as a whole. When the primary coil is driven with a resonant frequency of the secondary side, the phases of the magnetic fields of the primary coil and the secondary coil are synchronized. As a result, the maximum voltage is generated on the secondary side due to the increase of the mutual flux, and the efficiency is relatively improved. Another possible solution is magnetodynamic coupling. In this method, power is transmitted between the two rotating armatures, one in the transmitter and one in the receiver. The transmitter armature is turned either by or as the rotor of an induction motor, and its magnetic field exerts torque on the receiver armature, turning it. The receiver armature produces power to drive the load by turning an electric generator. It is claimed that this technique can transfer power over distances of 10 to 15 centimeters with a high efficiency of over 90%. With almost 200 years history, wireless power transfer still has a long way to go. There are still many existing problems to solve, for instance, the energy loss during each stage where energy is transferred to different forms. But one thing is sure, that is, wireless power transfer will definitely bring numerous possibilities to the future, whether it's for medical implants or vehicles.